Hi guys, you are welcome once again to the Smart Way lectures on the Science Ambassador series. This is a series of lectures we are running on all the areas in science. And today we are here with you to continue on thermochemistry, also called energy changes. Now we are going to look at the thermochemical laws, that is the 3 laws of governing thermochemical reactions. And so that if you want to solve a problem, then it means that you have to obey or observe these laws. So the first law, we have the law of conservation of energy and mass. And the second one, we have the law of reversibility, that is in thermochemical reactions. And we also have the Hess Law, that is the third one. And we are going to look at each of them briefly, and then we will begin to take you through some questions. Okay, very simple. Now, the law of conservation of energy and mass. This is a very simple thing. Good. Now, this law states that, and it itself is the first law of thermodynamics. It says that energy can neither be created nor destroyed in chemical reactions. Energy can neither be created nor destroyed in any in chemical reaction. This also relates to mass. Mass cannot be created nor destroyed in any chemical reactions. Now it means that the energy that you cannot destroy energy in what? In a reactant, or you cannot create energy. You can't create an additional energy of a reactant, and you can't create an additional energy of what? Of a product. Now the energy you begin with is the same energy you are going to end with. So for reactions that proceed from a reactant to product, the sum of all energy of the reactant must be equal to the sum of all energy of the what? Of the product. That's what it means. So that the total energy in the system become constant. Okay? So that the total energy of the system become constant. This again is saying that energy cannot be created nor destroyed in chemical reactions. That should tell you that it means that you cannot add additional energy to the reactant, and you cannot also add additional energy to what? To the product. The energy that was there before in the reactant, that is in the bond, that is the same energy that we are going to measure in the product. So basically that's what we are going to do. So this is a simple demonstration. Now if I have hot water, okay, at a temperature of 30 degrees, and I also have another hot water at a temperature of 30 degrees. Now each of these systems are hot. They have their own internal energies, okay, that is 5 joules each, okay, at this particular temperature. Now if I add these two hot water, okay, now I'm supposed to get equal amount of energy, okay. I'm supposed to get equal amount of energy, okay. So basically what I mean is that the energy of the reactant, that is this and this are the reactants here, that energy is not going to increase or decrease. It's also going to be the same. So this and this are the reactants. I'm starting with 30 grams of I'm starting with 30 degrees, and also 30 degrees, and the internal energy is 5 joules and 5 joules. Now if I add hot water to hot water, the hot water is just going to increase in hotness, and so the temperature is going to double up to 60 degrees, okay. And so the 5 plus 5 will be the same as 10. That is, the energy of the product will become the same as the energy of the reactant. So that's what it means, that you are not going to increase or decrease energy that you start with. The energy that you start with from the reactant is the same as the energy that you're going to end with. And so this is the proof of it. When you add hot water to hot water, the resultant become hotter. Have you gotten that? So that is going to double. That is, if you are performing this experiment in an isolated system, okay, that is what's normally called the adiabatic system that can conserve heat, that do not allow heat to move to the surrounding. You are going to get the same energy in the system. Now the second one is called the law of reversibility. Now this is very, very important and essential to understand. Now in every chemical reaction, I told you that there's 2 possible ways for you to achieve every chemical reaction. Now the chemical reaction can start with absorbing energy from the surrounding, now to increase the internal energy of it. So you can either start a chemical reaction by allowing the reactant to absorb energy from the surrounding, and then to finish with a higher heat content, okay. Or a reaction can also occur spontaneously, that is naturally, by just giving off heat to the surrounding naturally, without any artificial without any energy being absorbed from the surrounding. The energy is automatically coming from from the reaction into the surrounding. And so there are 2 possible ways by which we can always achieve a chemical reaction. chemical reaction can be brought about as a result of one, absorbing energy from the surrounding, to progress, or can either liberate energy to the surrounding. Now, so there are two ways, but each of these reactions, we can reverse it. In all reactions we can reverse it. So for example, now if you allow hot water to cool down, you would realize that it is going to give off energy to the surrounding. So hot water, if allowed to cool, will give off some amount of energy to the surrounding, and because it is a liberation energy, it is indicated as what? Negative. So here, from here, negative 10 kilojoules per mole is given off to the surrounding, through what we call the exothermic process. Now the water here is now cool, the water is now cool, but it started from what? From here. And so this is one way, by which we can represent the reaction. This one way, that this is what we call the exothermic reaction, where the hot water begins by giving off heat to the surrounding and then ending up with a lower heat content. The sign is indicated as what? Negative, because it is rather working on the surrounding by giving heat to the surrounding, and so it will finish with a lower heat content. And so here will become that. Now you can also, there's a possibility of reversing the whole thing. The cold water can also become hot, by the same measure of energy, by the same measure of energy. But in this time around, you are going to supply heat to the cold water in order to become hot. And so it is possible to reverse a thermochemical reactions. It is possible to reverse a thermochemical reaction only if you obey the conditions that for an endothermic reaction, for exothermic reaction to be reversed, then it means that you have to add energy, to the reactant in order to become the product again. So again, I'm saying that it is possible for us to reverse every thermochemical reactions. Every thermochemical reaction only occur from either exothermic or endothermic. Now this particular reaction that I've started with is an exothermic reaction, which occurs spontaneously by giving off this quantity of heat to the surrounding, from hot to cold. Now you can also make the cold water to achieve the same hotness. By this time around, this is going to absorb energy from the surrounding. Now the absorption energy, is indicated as positive, and so it's going to take 10 kilojoules per mole from the surrounding in order to become hot again. This time around, what have you done? You have reversed the reaction. The product in this case here, the product of this exothermic reaction become the reactant in this case here. So here, what do we mean? So here I have what to call the what? Let me indicate it here. I have what to call the what? I have what to call the what? The reactant here. So this was my reactant I started with. This was my reactant I started with, and then this was the end of my reactant, that is the product. Have you gotten that? And then I use negative 10 degrees to bring down the hotness to the coldness. Now I want in the second case, I want to reverse the reaction. By reversing the reaction, what do I mean? Now I want the cold water to become hot. It means that I have to supply energy from the surrounding. That is, the cold water is going to absorb energy from the surrounding. And so my cold water here, my product here become my reactant here, because it's going to now start a reaction. It's not going to start, and then it's going to end up to become the product. So you see what I'm trying to do over here. Now reactant is becoming product, and product become reactant. Now this is possible for you to reverse, provided you obey the laws. If you want an exothermic reaction to become endothermic reaction, then you have to supply energy to the opposite side in order to achieve the reverse side. And so the second law of thermochemical reaction states that it is possible to reverse any thermochemical reaction. It is possible to reverse any thermochemical reaction provided the sign of the enthalpy change, is reversed with the magnitude of the sign remaining the same. So it is possible to reverse every thermochemical reaction provided the sign is changed to indicate whether it is exothermic or endothermic. Now with the magnitude, however, remaining the same, it means that we are not going to change the amount of energy. The same energy that was lost is the same energy that is going to take, and so we are not going to change the the energy. Rather, we are just going to change the sign. The sign will just to tell you that it started with endothermic reaction, and now it started with endothermic reaction and ending with exothermic. But right now it is reversing to become endothermic to exothermic. And so that is what it means. So you can see from here that I've written exothermic reaction and you have written what endothermic reaction. I've been able to reverse the sign. So how do we represent that? So quickly, let's take a typical example of that. Okay, so this one, it is the same as this. So it's the same as this. I have A. Okay, I have A substance becoming B by exothermic process, giving off heat to the surrounding, and this heat that it gave was what? Negative 10. Now it is again possible to, from here I have what's called my reactant, and here I have what's called my product. Now it says that it is possible for us to reverse it, and here the enthalpy change. Here the enthalpy change is what? Is negative 10 kilojoules per mole. That is energy given off, okay, from transforming A to B. That is from the what? From the hot water to cold. So let me indicate here from hot to what? To cold. Okay, that's from hot water to cold water. Now it is again possible for us to what? To change the cold water back to hot, and so I'm going to get the B, okay, can be reversed, and then I can achieve the same A. I can achieve the same A over here. I can achieve the same A, and so I'm going to get what to call the cold water here. If it wants to become hot, then it means it has to what? Absorb energy from the surrounding, and so the plus sign will indicate that it is taking up energy from the surrounding. So it is endothermic process, and so here the enthalpy change, okay, is the same as plus. This time around is plus because it's taking what? Energy from the surrounding. It's plus because it's taking energy from the surrounding. So I'm going to get this mole per watt, and then that's kilojoules per mole. So that is it. So the second law says that it is possible for us to reverse any thermochemical reactions, okay, provided the sign of the enthalpy change is reversed. The magnitude, however, remains the same. The amount of energy that it liberated must be the same as the amount of energy that it must absorb. And so the figure must be the same, but the sign must change to indicate that the reaction has been reversed. So basically that is it. Now quickly let's look at the Hess Law. Let's look at the Hess Law. So quickly let's go to the Hess Law. So we are on the Hess Law now. Now what is Hess Law saying? This is very interesting and very simple. Okay, now suppose you have a problem, you have camphor, and you want to transform camphor at a particular temperature, that is same temperature, from solid to gas. Okay, now you need some amount of energy in order to take the camphor from solid to gas. Okay, so the initial state here is a solid, and then here the final state. So we have what's called the initial state. Let me write it here. We have what's called the initial. I'll call the initial state. The initial state is you have what's called the initial state, that is a solid state, and we have the final state. I will call the final state. So here I want to transform. I want to call the final state. Okay. So here I want to transform the solid from the initial state. That is, I want to transform the camphor from solid, from its initial state, to gas. Okay. Now there is some amount of energy that I require, okay, to change the camphor from solid to gas. Now, so, and I can achieve this one by just one step reaction. Okay, I can achieve this by just using one step reaction, by allowing the camphor to just move straight into the gaseous state. Have you gotten that? So I can achieve this by one step reaction. Now, and again, I can also first of all melt the camphor to a liquid before now changing it to a gas. Now, so here I can see that we have two-step reactions. So here we have two-step reaction. I can do it straightforward by changing it to a gaseous state by one-step reaction, and I can also change this one from the solid to gas, okay, from solid to liquid by melting, and then again by what? Boiling to what? To this one, okay, to a gas. So I can use two-step reaction to also achieve this. Now, in the Hess Law, it says that provided the initial and the final state are the same, the total enthalpy for a reaction is the sum of all the individual enthalpies for the stepwise reactions. Is the sum of the enthalpy change for all the stepwise reactions. Here I have one step, I have what we call one reaction moving from solid to what? To gas by one reaction. There is an amount of energy that I can use to change the camphor from solid to what? To gas. Straightforward. Now, but I can also use two-step reaction to also change the solid, okay, to what? To gas, by moving the solid back to liquid and then moving the liquid to what? To gas. Now these are two-step reaction. If I want to pass this way, I'll use two-step reaction. But if I want to pass this way, I'll use one reaction. But here, the one reaction has the initial state to be solid, and then the final state to be gas. And then the two-step reaction also have the same solid what? To gas. So Hess Law is saying that provided the initial and the final state are the same, then the enthalpy change for a particular reactions like this moving solid to a gas is the sum of the enthalpy change for all the what? The stepwise reactions. So if there are 100 steps that it took for moving solid to gas, then you have to add all the energies that are what? Are involved in the what? In the process, okay? Are involved in the process. So this is what we mean by Hess Law. Now this is also another illustration that now moving a substance from A to B, okay, it is the same as moving from A to X, X to Y, and back to B. Because you see, the Hess Law is saying that provided the initial state and the final state are the same, the initial state and the final state A and B, okay, are not changing, then it means that anywhere you pass through, Hess Law doesn't care about that. It all cares about adding all the pieces together for moving from A to what? To B. You can do it direct by using one step, okay, and you can also use multiple steps to also achieve the same way, okay. This is very simple. When you are leaving your house to your school, now the school destination and your house destination are fixed, they are not changing, but you can pass through so many routes. If you use shortcut, okay, the energy that you waste, okay, for the shortcut is the same as the energy that you take when you go through several steps. And so Hess Law is telling you that always go through the shortcut, that is the straightforward, and to get the energy. But if you pass through a lot of energies, if you pass through a lot of pathways, the sum of all the energy that you took will be the same as the one-step reaction moving from A to B. So once again, the Hess Law, which sometimes we also say that the Hess Law of constant heat summation, okay, but you can just simply say Hess Law. They say that provided the initial and the final state of a reactant and the product are the same, the total enthalpy change for the reaction is the sum of the individual enthalpy change. So therefore, if I want to do this mathematics in the first one, I'm going to get this. I'm going to get this one. That is the total is equal to how many steps here? So I have what to call two steps. That is the enthalpy change of the first step by moving it from the solid to liquid, and then I'll add it to the second step, okay? That is this step. So it means that if you can do it straightforward, and you can also use two pathways to achieve the same process. For here, it is also the same as the standard enthalpy chain, okay, is the same as, okay, the enthalpy, the first one, okay, that is the enthalpy chain along the first one, okay, plus what? The enthalpy chain for the second one, as this second one, which is this. So this is the first one, now this is the second one, and now I'm writing the third one. So now plus the what? Plus this. So provided the initial and the final state A and B are the same, provided the initial and the final state are the same, okay, the total enthalpy change, okay, moving from A to B is the same as the sum of all the enthalpy changes, okay, along all the other pathways, okay. So that is very simple. Other book you can also say that for a reaction that takes place in several stages, for a particular reaction that occurs in several stages, the sum of the enthalpy, okay, is the total enthalpy change is the sum of the enthalpies of all the individual stepwise reactions, okay. You can also say that, and you can also summarize by saying that the enthalpy change for a particular reaction is independent of the pathway, that it is free from the pathway. That means it's independent. Independent means that it is free. The enthalpy change is independent. It's not path dependent. That means that it doesn't depend on the route that you took. One step reaction can give the same answer, and multiple step reaction can also give the same answer. So it doesn't respect the path that you take along the process. We say that the enthalpy change for a particular reaction is independent of the path taken. Or if a reaction occurs in the several steps, like this particular reaction occurring in the several steps, the total enthalpy change is the sum of the individual enthalpy, okay, of all the stepwise reactions. So that is what it says. That's what enthalpy says. Let me give you a typical example. Now, in case in the lab you want to heat carbon, that is graphite, that is the thing inside our pencil. So graphite, that is graphite. That's you want to heat carbon, okay, in oxygen. Now, when you heat carbon in oxygen completely, what happens? We are going to get carbon dioxide. We are going to get carbon dioxide gas coming out from the process. So here will also be a gas coming out. This is what's called a complete combustion. That is a one-step reaction, complete combustion. So complete combustion. Now here it means that you use what's called 1 mole. Now, so this is a complete combustion now, but you can also perform this reaction in so many ways. Okay. Now, depending on the quantity of oxygen that is there. Now you can divide the quantity of oxygen into two. Okay. I can divide the quantity of the oxygen that I use. Here I use 1 mole of oxygen. Okay, I use 1 mole of oxygen gas. Now if I want to do it in two-step reaction, then it means that I have to divide the oxygen into two. And if I do that, it means that I have that quantity of carbon, meaning that I'll use half, okay, quantity of oxygen that I use. And if I use half quantity of oxygen, what happens is that I will not get carbon dioxide. I'll get a compound called carbon monoxide, which is this. So we are going to get carbon monoxide, which is this. And this carbon monoxide is a poisonous gas. Monoxide is a poisonous gas. Okay, so the incomplete combustion of carbon generates what's called carbon monoxide, which is a poisonous gas. Now, if you can continue the reaction. So here you can continue the reaction again by taking the carbon, okay, by taking the quantity that is left here. So the carbon monoxide, which is also a gas, this is also a gas, okay. Then you can add the remaining oxygen to it. Okay, you can add the remaining oxygen. You remember we started with 1 full oxygen, and now you are using half. Now the next one you also have to use half. So the half oxygen, and then when you add the remaining half oxygen to the monoxide, you are now going to get carbon dioxide. You are now going to get carbon dioxide. So here you can see from this reaction that here the initial state. Here you can see from this reaction that here the initial state. Here this is a solid. You began with a solid, okay, and we began with 1 mole of this. So solid and 1 mole of this, and then you are ending with You are ending with this. So here you are ending that, and then you want to divide it into into 2 steps. So let's say steps. You want to divide it into steps. The first step is by using half oxygen and burning by using half oxygen and burning it with the quantity that is there over here. And here the first one you get carbon monoxide, okay. And the second step, you take the product, that is the carbon monoxide, that is the remaining whatever form from the remaining. You take it and then you add the remaining half oxygen to it. So then that will also generate carbon dioxide. So from here, when you add everything, you can see that you are still obeying the same thing over here. Here, what do? When you add this plus this, here when you add the 2 reactants, you can see that here this and this will give me what? 1 full mole of oxygen here, okay, which is the same as here. And when you add this plus this, when you add this particular one plus this particular one, this reactant will cancel this product over here, and so we are just going to be left with what? We are just going to be left with this. Have you gotten that? We are just going to be left with this, and then here we are going to get what to call this also plus this. We are going to get what? This over here. So when you add all the stepwise reaction, that is the energy. So the energy that will come out from M1, that is the change in enthalpy of H1, and then the change in enthalpy of what? Of A2, of H2, okay. That is H2, okay. When you add all that, okay, H2, when you add this reaction plus this reaction, you still get your same thing. So if assuming that the change in what? Enthalpy for the first one was T, okay, then it means that the stepwise reaction, which we use 2-step reactions, we are going to get the change in enthalpy. We are going to get the change in enthalpy. That's the total change in enthalpy, the same as the what? The change in what? The first one. That is the first one plus what? Plus the second one. That is this plus this. Okay. So that's what it is. So in Hess law, what basically happens is that when you start with a particular reaction whose reactant and product are in the same state and with the same quantity, and if you want to devise what other reaction route for it, that means that you can only add the enthalpy changes provided the initial and the final state are all the same. So here I started with solid carbon, and this is my solid carbon. I use half oxygen, okay, and then I got monoxide. And then in the second step, I took the monoxide and I added the remaining half oxygen to it, and then I got carbon dioxide. And I wanted to make sure whether it is conforming to what I started with. So I added the 2 reactants, and this cancelled this one, which is a reactant, cancelled this, which is a product here. And then I added this plus this, that is this one added to this. I'm going to get this, and then half oxygen plus half oxygen, we are going to get 1 more oxygen, which is the same as here. And then I add this to this and I'm going to get that. So that means that the energy evolved during the formation of the carbon dioxide, that is the H1, plus the energy involved during transforming the monoxide to carbon dioxide A2. If I add the 2 reactions together, the energy together, I'm going to get the total enthalpy for the reaction. So this is what Hess law is saying. So we'll end our lecture here, and in our next lectures we'll begin to take more questions and more questions and more questions. Thank you very much.